All right, guys, so we're going to go ahead and do a video over chi-square. Originally, I planned on being there to teach it to you, but it turns out we have this luncheon type thing up here at the college. And so I'm going to do my best to explain chi-square over the video. I do want to remind you that you could also watch some videos, like there's a Bozeman science video. You could also find this on Khan Academy. We're not going to do a lot of problems. In fact, we're not going to do the ones where you have to do a lot of genetics for it. We're just going to be doing just a couple over a basic 9:3:3:1 ratio. And so I have my handy dandy little notepad here. It's kind of the best setup I can find for this kind of situation. And so in the video over the fruit fly, chi-square was mentioned. And so just to kind of give you a general background, it's a statistical analysis test, and you are literally solving for the variable chi-squared. So in no place will you be taking the square root of anything. Like your answer is going to be chi-square equals. And so what it is it's called a goodness of fit test. And what it does is it takes an event based on probability, and it compares how close is what I got in real life to what I should have gotten based on probability. And we could do this with anything that is a probability. We could use spinners. I used to have some colored spinners that had 6 colors on them. And ideally, as long as it was a fair spinner, I could get each color 1 out of 6 times. Okay, they all had the same probability. Now, one example of what we could do a chi-square test for is just a basic coin toss. And we'll do this test here in a minute as an example. So let's say that I flipped a coin. Well, hopefully you know that I have a 50% chance of getting heads and I have a 50% chance of getting tails. And so what if I flip that coin 100 times and I got 60 heads and 40 tails? Now, what the chi-square test does is it's literally going to compare these values to what I should have gotten statistically. And so if I had a 50-50 chance in a perfect world, if I flip that quarter 100 times, I should get 50 heads and 50 tails. So what the chi-square test does is it compares what I actually got, the 60-40, to what I should have gotten. And it gives me a numerical value, the chi-square value, which I will then look up on a statistic table, and I will use that to determine, do I accept those results and say that that's a fair coin and that it's completely acceptable to get 60-40? Or do I say, really, that's too far off from what I should have gotten? That must not be a fair coin. And so that's what the chi-square is all about. Now, what we're doing is we're applying it to genetics. And so in genetics, we've done Punnett squares. And we know from Mendelian genetics that there are expected ratios. Like the P generation was always 2 true breeding. And in the F1 generation, I should get 100% dominant. And then when I cross 2 F1s, I get my F2s, and I always get that around 3-1. Now, if we're looking at dihybrids, if it's a dominant recessive relationship, I should get a 9-3-3-1. And so part of this does come from your knowledge in genetics, and that you should know what these expected ratios are. But when in doubt, you could always do a Punnett square to figure out what your expected ratios should be. Now, to make this a little simpler, and because we don't have a lot of time, we're just going to be doing basic Mendelian traits. Okay, we're not going to do any sex-linked or anything like that. But ideally, you could use this method for any type of cross. Now, this was included with the fruit flies because in a fruit fly experiment, essentially you're trying to determine how is that mutant inherited. So remember, you always had a wild type, like red eyes is wild. Well, you might cross that with a white-eyed to see how is the white inherited. Because sometimes the mutants are inherited as the dominant trait, sometimes the mutants are inherited as a recessive trait, sometimes they're autosomal, sometimes they're sex-linked. And so really the purpose is that we would be using this to kind of support our conclusion that a trait is inherited in a certain way. But we're just going to practice the math, okay? So on this next little paper here, I'm just going to go ahead and take this one off. So these are kind of the basic steps for doing a chi-square test. And so what you're going to be given always, and you should have a handout that looks like this, okay? And all we're going to be doing is there's a problem that's already been done for you on the front, and then we're going to be taking a look at this sample problem on the back, okay? Now, in the past, if I was there teaching you directly, we'd be doing some of these fruit fly problems, but just for time's sake and because, I don't know, because I'm not there to teach you myself, we're just going to look at a couple of samples. Now, be prepared to see a chi-square on your test, and be prepared to answer questions about the chi-square in terms of like multiple choice. But it will only be problems like the two that we're going to look at today. So when you're doing a chi-square test, first of all, what you need to know is that you're always going to be given the observed values, because the formula, which I took this off, the formula is right here, and you will be given the formula on the test. So you have the O and the E, and then you have this funky E symbol. Okay, so the formula is the sum of the observed minus the expected squared divided by the expected. And so what we're going to look at is how close are our O's, the observed values, to the E's, the expected values, which is what we would have gotten if it were perfect and it met all of the rules of probability. Okay, so in any given chi-square problem, you're always going to start off with the observed, which is what you got in real life. Okay, so if you look on this front paper here, they gave you the observed over on the left. Okay, essentially what it says up here is we are doing a goodness of fit test. We are looking at two traits. This is a dihybrid cross. We have round versus wrinkled, where round is dominant to wrinkled, and we have yellow versus green, where yellow is dominant to green. Now, because this is a dihybrid, it tells us that what we're doing is we're testing a 9:3:1 ratio. And so what we're going to look at is what's called a null hypothesis, okay? For every chi-square, we are either going to accept or reject what's called a null hypothesis. So we're going to take our observed, we're going to compare them to our expected, and once we get that value, we're going to use that to determine if we accept or reject. Now, what the null hypothesis states is that there is no significant difference between the observed and the expected, okay? It's saying that the numbers we got in real life are close enough to the expected for that to be a fair test or a realistic outcome, all right? So like if I'm testing that these are just dominant recessive traits, if I'm testing a 9:3:1, then if I accept, I'm saying those are numbers that we should get, okay? Those kind of fit that 9:3:1 ratio. If I reject, I'm just saying, nope, that doesn't fit that ratio. There must be some other type of inheritance going on, okay? And that's as far as we're going to go. We're either going to accept our null hypothesis or we're going to reject our null hypothesis. So if we accept it, we're saying, yeah, there is no significant difference between the numbers I got and what I should have gotten. If we reject the null hypothesis, we're saying, yeah, there's a big difference. It's big enough for us to say this isn't the inheritance pattern. So for your test, you're going to be given the observed. And so for this one, on your paper, it says that you got 315 round in yellow, 108 round in green, 101 wrinkled in yellow, and 32 wrinkled in green. So we're going to compare these numbers to a 9:3:1 ratio. Okay, so this is what I'm always starting with, is the observed. Now, the second step is we're going to have to calculate the expected. And so in order to calculate the expected, the very first thing you should do, if it's not already done for you, is you must total the observed, okay? Because we've got to figure out how many should we have gotten if it went perfectly, if we got exactly a 9:3:1. And so you can see that on this paper right here, they've already totaled it for us. So we added those numbers up for a total of 556. So that's going to be the very first thing you do with your numbers, is if they're not already totaled for you, you have to total them, all right? So now that takes us to step 3. We're always going to be given our O's, but we are going to have to determine what the E should have been, all right? And so what you do is you take that expected ratio. So in this case, we would be testing the 9, 3, 3, 1. Now, 9 by itself is not a ratio. Okay, so I want you to think about a dihybrid cross. How many boxes do you have in a dihybrid cross? Okay, so kind of picture it really quickly. It's a 4 by 4 box. And so we have a total of 16. So when I say 9, 3, 3, 1, I'm saying 9 out of 16, 3 out of 16, 3 out of 16, and 1 out of 16. Okay, so our ratio would be those fractions. So I take my total, which in this case was 556, and what I have to do is I have to figure out my E values. And so to get my E value for the first one, I do 9 out of 16 times the total, which was 556. And once again, this front page, it's already been done for you, so you can always go back to this paper and kind of see the steps. So to calculate my E values, I multiply the ratio, the expected ratio, times the total. And so you can see I got 312.75. So just at a glance, if I got 315, in perfect world, I would have gotten 312.75. That's pretty close. I do the same thing for each one. So I had 4 different possible phenotypes, so I'm going to have to come up with 4 different E values. And every time I take the expected ratio, the fraction, and multiply it by the total. So you can see that they did 3 out of 16 times the total, 3 out of 16 times the total. You only have to calculate that once. And then 1 out of 16 times the total. And so we were given our O's here, and then you are going to have to calculate the E values. Okay, so you take the expected ratio and multiply it by the total. Okay, so that's why you have to find that first. Now, once you get your O's and your E's, this is where you plug it into the formula. Okay, and so if I had 4 different phenotype possibilities, I'm going to have 4 different sets of values. And this is where the sum of comes in. Okay, so I take my first number, my observed, minus the expected. I square it. That gets rid of the negative if there is one, divided by the expected. And so this is already done on your paper as well. Okay, if you look down here, you can see that each one of those is written out. So I did that for each one of my O's. Observed minus expected squared divided by expected. Observed minus expected squared divided by expected. And so you just have to plug those numbers into your formula. Now you guys have the fancy calculators and you have access to calculators in class. Use the parentheses. I would highly recommend just typing it in exactly as you write it. You are going to have to write it out if you want credit. You can't just do everything in the calculator. We've got to see what you plugged in to see if you did it correctly. Okay, so you're going to have to write out all of this long formula. So in this particular case, you had 4 different things that you were adding together. And that's why you get this sum of. Okay, so we had 4 events, and you're going to have to add each of those together. I highly encourage you just to plug it all into the calculator in one long problem. Just use the parentheses where you need to, around the observed minus expected squared. And then it will follow the order of operations, and you don't have to worry about getting some weird numbers. Okay, so once you plug it in, whatever value you come up with is your chi-square value. And so in the case of this problem here, your chi-square value was equal to 4. No, I take that back. Your chi-square value was equal to 0.47. Now, at this point, what we have to do is we have to take this number and we have to go to a statistical analysis table. And so on my lesson about fruit flies, I showed you a table and it was really big. It had a whole bunch of numbers on it, okay? Now, what you have in your packet right here on the back is a smaller version of that table. It's the same numbers, it just doesn't have every single percentage and every single chi-square value that big table did. But it's pretty much the exact same table, okay? So what you have to do, because remember we're trying to decide, do we accept our hypothesis or do we reject our hypothesis in saying that there is no significant difference between our observed and expected. Now, I'll just tell you right now, you shouldn't be getting enormous numbers here, okay? Because if we got enormous numbers, we wouldn't even be testing that data. our numbers should be relatively close together. So if you're coming up with a huge number, you've done something wrong, okay? You should be coming up with a number that is a decimal, or if it is a whole number, it's probably not going to be much higher than 10. Because more than likely, if we're getting numbers like that, we've done something wrong, or we're testing something that we really shouldn't be testing, okay? Because our numbers should be close together if we're testing that ratio. I hope that makes sense. So we got 0.47, okay, for that problem on the front paper. And so here's how we use the table, all right? And this is mentioned in the video, and hopefully I went over it in the video. If you go to Bozeman Science and watch that, you should see it there too. But in this table, you might want to take your paper right now, and I got a little crazy with my bold line, but 0.05 is my cutoff, okay? This is what's called my critical p-value. And 0.05 represents 5%, okay? So you see this right here? You might want to draw a big bold line between the 0.05 and the 0.01, because this is going to be my cutoff of how do I decide if I accept or reject. Now, over here, and I can't really explain this, I'm not a mathematician. Someone who is a mathematician might be able to explain it. But your degrees of freedom, when you're using the table, you always look up however many events you had minus 1, and that's your degrees of freedom. So in this problem that we did on the front paper, we had 4 different outcomes, okay? And so my degrees of freedom would be 4 minus 1. So I would look up on the table degrees of freedom 3. If I only had 2 outcomes, I would look up degrees of freedom 1, okay? And so what you're going to do is my chi-square value was 0.47. And so I look up degrees of freedom 3, so right here, and I try to find where would 0.47 fit on this table. And so it would be right here. There's my 0.58. Now, this up here represents 90%. That represents 50%, that represents 10%, and that represents 5%. Now, we accept anything that is 5% and over. And what that's telling us is that we would expect to get those values for a test like this at least 5% of the time or more. So as long as your chi-square value fits in the area of the table that is greater than 0.05, we're going to accept. Now the only time we would reject is if our value fell on the opposite side of 0.05. Okay, so see how these numbers over here are all big, like 6, 9, 11, 13, 15? So as long as your chi-square value fits to the left of the table, right here, my critical p-value, as long as my value is on this side of the table, I'm going to accept. And what I'm accepting is that there is no significant difference between what I got and what I should have gotten. Okay? So now let's just do a simple chi-square. We're going to walk through the process. We're going to test out that coin flip. Now if we had time, we could actually get out real quarters. We could do these coin flips and we could test for ourselves. But I told you that if we flipped a coin 100 times, we got 60 heads and 40 tails. So we're going to test the null hypothesis, okay? The null hypothesis is always the same, that there is no significant difference between observed and expected. Okay, this is what we're going to accept or reject. So let's go back to our steps. Once again, we're always given the observed. So if we accept this, we're going to say that's a fair coin and that's normal. Or if we reject it, we're saying that's not a good quarter. There's something wrong with that quarter. There's something off about it. And this is not normal results. Okay, so this is a numerical way to determine yes, that's close, or no, that's not close. Okay, So step 1, we're given the observed. Step 2, we total the observed. Now this is going to be a pretty easy one that you can do in your head, but I would still go through the process. So my total was 100. All right, now my next step is to apply my expected ratio to my total. So these were my observed. What I need to get are my expected. Okay, so here's how I do that. For a coin flip, my expected ratio was 1/2, and I would recommend using fractions. So I do 1/2 times my total. Now we know it's 50-50, but this is how you would calculate it. And I have the same expected ratio for the tails. You may not always get whole numbers, you may get decimals, okay? So there are my expected values. So they're given my observed. I have to calculate my expected. And my next step is to plug it into the formula. So chi-squared equals observed minus expected squared divided by the expected plus, remember we have to do the sum of, I do my next event, I did those backwards, 60 minus 50 squared because of the square it will come out the same, but sorry about that, y'all. So observed, so 60 minus 50 squared divided by 50, observed minus expected squared divided by the expected. So that's just 40 minus 50, sorry about that. All right, so now I would go to my calculator and I would plug it in. Okay, so I don't have a fancy calculator here, but this would be 10 squared, so 60 minus 50 would be 10, squared would be 100, divided by 50, so that would be 2. And then I would get the same thing over there. That would be a negative 10 squared, so that would be 100 divided by 50, so that would be 2. So what I get is a chi-square value of 4, okay, 4.0. And so this is the number that I'm going to take to the table, okay. Now the first thing I need to know is what is my degrees of freedom? Well, I had 2 events, right? I either had heads or tails. So my degrees of freedom is however many events I had minus 1. So for my degrees of freedom on my table, I'm looking up 1 degree of freedom. And then I'm looking to see where this number fits in my table. So when I come to my table, I've got 1 degree of freedom here. And I try to see where 4 would fit, okay? Now, my 0.05 value is 3.84. And since 4 is higher than that, it would be on the other side of the table. And so in this particular scenario, I'm going to reject. So once again, I go to my table. My 0.05 value is 3.84 at 1 degrees of freedom. My number came out greater than that. And so if my number is greater than that 3.64, that means that I would expect to get that less than 5% of the time. And so I'm going to reject, okay? I just have to figure out where does it fall. Is it 5% or greater? I accept. Less than 5%, I'm going to reject. So in this case, I would reject. And what that means is there is a significant difference and there's probably something off about that coin. All right, so all you guys need to do, and Miss Petty's going to be there to help you, is you have a sample problem that you are going to do right here, okay? Now, if you need more help with chi-square, once again, there's some videos, there's some Bozeman science. You could look up some more practice problems, but we're not even going to look at the fruit flies because you don't really have time to learn how to do those. There's a little more genetics involved with those. And so all you need to be able to do is test a problem like this one on your paper. Now, what it says is a large ear of corn has a total of 433 grains. Now, be careful because this one started off by giving us our total. It says there's 271 purple and starchy. There were 73 purple and sweet. There were 63 yellow and starchy, and there were 26 yellow and sweet. So once again, these numbers here are my observed. They always give me my observed values. Our first step would be to total. Now, in this particular problem, they actually told us in the very beginning, they said we have a total of 433 grains. But if they didn't tell me that, my very first step would be to total all of these. So 433. And it tells us in the problem, we're going to test a 9:3:3:1 ratio. So to get my expected values to plug into my formula, I'm going to have to apply my ratios to my total. So 9 out of 16 times 433, 3 out of 16 times 433, the same thing there, and then 1 out of 16. So remember, this is a 9:3:3:1. I could do this with a monohybrid, and then I'd be testing a 3:1 ratio, okay, because I'm looking at my values in my F2s. So what you're going to have to do is you're going to have to calculate that out, and that will give you your E values. Now, just to know if you're doing things right, these E values should be somewhere in the ballpark of the O values, somewhere close, okay? If you're getting a number that's way off, you're probably multiplying the wrong thing. One common mistake is students will multiply the ratio times the observed. And then you're just taking a fraction of what you got, and that's totally wrong, okay? You always have to apply the ratio to the total. Because if I got 433 in a perfect scenario, how many of those 433 should have been purple and starchy? Okay, so what I want you guys to do is I want you to finish out this problem. If you have any trouble, you can look on the front. It kind of showed you how they worked out that problem. You can always ask for help from your neighbor or Miss Petty. Now, I'm going to tell you that your chi-square value comes out to be like 8.0 or 8.1, something like that. And so, you know you've done it right if your value comes out to be that, okay? I think I actually looked it up on the computer, but it's either 8.0 or 8.1. I can't remember for sure. So what you're going to do is you're going to have to calculate your expected first. Then you will plug it into the formula, O minus E squared divided by E. You're going to have to do that 4 times. Once you calculate it out, and please do it, practice doing this in your calculator, because that's part of the problem is students won't plug it into the calculator properly. So make sure that you can find your E's, you can set up the formula. You're going to have to show your work on the test. You should come up with 8.0 whenever you do your math. Now this is the number that I will take to my table. I had 4 events, okay? I had 4 different phenotypes or 4 different outcomes. So I'll look up degrees of freedom of 3, 4 minus 1. And that I will look for the number 8 and see where it fits. If I'm in the range that is greater than 0.05% of the time, I'm going to accept. If I'm over here on the other side, I'm going to reject, okay? So I'm sorry I'm not there in person, guys. I'd love to see you and talk to you in person. The only thing you'll be expected to do on your test is A, answer questions about chi-square, and you had notes on that in your fruit fly notes. And B, you can expect to see a chi-square problem, but it will be similar to one of these 2 that are in your paper, the one on the peas or the one on the corn. You'll be expected to test that 9-3-3-1, okay? Now, if you want to challenge yourself and you have the fruit fly paper, you're welcome to try those out, but it's not expected that you know how to do those. Those you have to kind of work through the different generations. So what you'll be seeing on the test is a problem like that we saw today, okay? So if you have any questions, watch videos, ask Miss Petty, get some help. I know your test is coming up soon. Feel free to email me as well if you have any questions. And hopefully, guys, I'll get to see you soon. Y'all have a great day.